I mean, this is, again, some sort of examples of how far you can get with this. So this is from this Newman paper. This is the number of boards that directors sit on, right? So a lot of them sit on just, did he do this? Yeah, a lot of them just sit on one, right? This is a linear thing here, right? So there's a director who's just on one board. There's someone 9 boards up here, there's someone here. And then the number of members on a board, though, so this is a log scale. This is kind of exponential, right? Decays pretty strongly. But this person's a pretty interesting character, right? There are 9 boards. This one's on, we've got a couple of, what's this, maybe 3 on 8, 7 boards, actually. That's a lot of potential for information and so on to flow through. And then there's this kind of typical average here of about 10 per board, but some are bigger. Yeah. I guess there's a board of 2. Yeah, right. No, maybe that's a 0. No, it's a 1. It's on a log scale, right? So yeah, okay, yeah. So you could start with that. This is the idea of this. We're going to start with these observed underlying degree distributions, and then randomly wire them up and see how far that departs from what we've observed for random networks. So boards have 5 to 15 directors, that's that kind of average there. And then we're going to presume all of this bipartite structure and then generate these things. So you do this, and then you start looking at the induced networks. So this is the company directors, movie actors. This is co-authors in 2 academic areas. And you get so this is pretty good, right? So these are the clustering coefficient. This will be the Newman one, the triangle version. This is the theory, and this is the actual, right? So we're just going to take degree distribution for, in this case, directors and boards. This is the degree distribution for movies, right? You just go through all the movies and count up. This one has 7 actors. This one has 23, right? Make a degree distribution from that. Look at the actors separately, count up all of the things, and then just randomly assign actors to movies. Do that and see how far away the resulting structure is from reality, measuring a couple of things. So the average degree, that's really kind of guaranteed a little bit, right? Because that should work out. So this is pretty good. That's a little bit off. But these numbers are really good, right? So it's very hard to make, this one's a bit further away. So there's something going on here that suggests that this is a bit different, right? These aren't really randomly wired up, and you can imagine there's more cohesion perhaps in co-authors working together in interesting ways, or the way that they kind of meet each other and so on. It gives you a sense here that these are just sort of thrown together, right? You're going to be in that movie. Of course, all of these things are collapsing in time, what are really temporal networks. So that's a whole other thing that people are still struggling to understand and do a good job with. Anyway, pretty good. So these are pretty decent matches. These are quite superb. So there seems to be right, that this is a reasonable kind of model actually for those things. And so you go and look at motifs and so on, or look at some basic things in the real system and see how far what's the non-randomness of this thing, right? That's a question over and over, like way beyond networks, just in science in general, is you basically describe and find all of the randomness in a system, peel that back, and the structure is left in the middle. That seems to be kind of a persistent game. And you do need to explain the randomness as well. That's a real feature. So these are just some examples of the induced networks for this randomly wiring things up. So this is pretty good, right? So these are the dots here. Let's get this right. So the points of the real world data, and the solid line is the bipartite graph model. So that's a pretty weird distribution to fit well, right? Like this, this is what the model is actually producing. And this is what you'd get if you just had a Poisson distribution with the same mean, right? So if you just said, right, we're not going to actually connect through this. I'm just going to have some average degree and then randomly wire up the directors. Yeah. So that's a really spectacular, I mean, it just seems, I remember when I first saw this, it seemed kind of, I mean, I just sort of seeing it for the first time, I had no idea what was, I was like, what is going on? This is madness, which is presumably where you are now. Right. What's that? Yeah, so these points are the real things. This line is from saying we've got this distribution for the number of boards that directors are on. We're going to take that. So that's, yes. And we're going to take this as well. And then we're going to make a whole bunch of directors following that distribution. And we'll make a whole bunch of boards. And then we'll just randomly wire them up. We'll just do this thing. And then we'll look at properties of it. So this is the directors one. Really kind of spectacular. And then this is looking more, not just the average degree, right? This is the average number of, not just the average number of co-directors you have, if you're a director. This is probably the distribution of it, and it's fitting this thing super well. Yeah. Newman loves to have things in here. It's not in this one, but it says the standard errors are smaller than the symbols. Right. There's lots of little plots, and just that the standard error is smaller than the symbols themselves, right? Yeah. Okay, so this is pretty good. These ones aren't. You can see there's some departure here. This is on a scale that's probably obscuring things. You'd really want that to be on a log scale, because there's a tail. And the vertical to be on a log scale, because there's a tail there that's, looks small, but we know tails hide things. So it didn't work, so it doesn't work as well the other way, right? So this is a different thing. So this is the number of other boards this is the board connection side of things. So that one's not working quite as well. So you want it, right? So did not do as well on that side. So now, the game would be, there's something maybe, like the way the directors are assigned seems to be kind of random, but there's something else going on about these boards. And so the reason for this, and I don't know if, yeah, exactly, right? So this, we'll talk about assortativity later on. It's a simple idea, but it's a powerful one for networks, which is birds of a feather flock together, right? And it could be things like just a high degree nodes connected to high degree nodes or something like that, or it could be the characteristics of the nodes that make them sort themselves out. But this term wasn't used back then in this 2001 paper. It's the term that's generally used now, assortative and disassortative. So there's the directors tend to be on the same boards. So that's breaking this randomness thing. And what effect that might have on how the whole system works is interesting, right? It sort of dampens it a little bit, because you're not as, right? You don't have, this board and then everyone is on different boards, right? You're actually on other boards together. What does that mean? Does that sort of reinforce, it makes a stronger connection between those boards, right? So these two boards share 4 people. Does it make for collusion or better systems? I don't know. So you can do all sorts of other things, right? Contagion and so on top of it. But again, surprise. So this is a simple departure from random networks. Pure random networks are not going to model these things well at all, right? Or even not pure ones, but random networks with fixed degree distributions. Which we saw got us a long way for a lot of systems. So this is a really nice step beyond that. It introduces a very natural, real kind of aspect of a lot of systems in that there's context or something like that, right? That there is some sort of affiliation structure. And you can't, people certainly tried to like generate the director network from some sort of other, right? You have to have this. It just really is what's going on. Like if you wanted to get those levels of clustering, for example, from a growing network, it's much harder. It's a much harder, sort of weirder thing to do because this is these are pretty weird structures. You can't just sort of pull them out of you're not going to pull these things out of, right? You're really not going to pull these out of a box because if you think about, making like the movie actor one where you've got a movie, it's got 20 actors and you connect them all together, that's a huge clique of actors. And then you're going to have another huge one over here of 30, right? That's a really low entropy kind of structure. Even though we've constructed it actually from a pretty random sort of background, right? We made a whole soup up here and a whole soup up here, randomly wired them up, made a thing. So from that point of view, from the box of bipartite networks, right? Or bipartite affiliation networks, these are easy things to get out. But you're not going to get them out of the big box that just says networks, right? You're not going to get these things out. We know we're not going to get like the scale-free distribution ones out. Yeah. Okay. We talked about the. Okay, so that's we're going to stop there, right? I do want to talk about other things like diffusion and then contagion, and I'll couch all of those in terms of physical stories, which is much better. I think people will be happier. So thank you for enduring that. I'll fix up the little glitches I have in there. But we're getting that story to be better. Okay, let's have a therapeutic. Who is that? Well, who is this though? Totoro, yeah. There are various Totoros around the house, so.
I have a cat bus.
Right, we talked about the cat bus, yes. Right, yeah. Cat bus is great. Yeah, I remember actually going on Amazon and going like cat bus. When my kids were small, I'm like, we should get that. It's pretty expensive actually. Anyway, so this is my brother and sister-in-law's cat in Brisbane, Timothy Burt Dodd. Anyway, yeah, that really got at people, but gee, this cat is just ridiculous. Anyway, look at him. See? It's all right. So nice. Just nice. Pratchett's doing well, yeah. Okay, so that's a good place for that to stop. I want to say just a few little things here. So I've added more stuff, right? So now this will give you a little sense of where we're going to go. I'll talk about some version of this. I'm not going to put all of these things in here, but these are really, contagion is a big piece still. Structure detection is enormous. This is community detection. That's such a monstrous area. We're kind of at the point now where, and this will be a fun thing, we kind of have to build up a little bit to it. There are so many methods, and you're sort of, you guys are now, if you're working with networks, you'll be in some environment and there'll be like buttons to click and so on. So fine. But you kind of need to know which algorithm, what they're trying to do with these things, right? They're trying to find modular structure if it exists so they can kind of show it and present it. I mean, because it's real, it's a real thing. These pieces may or may not get touched on, but we'll certainly have to talk about some simple pieces that build up to that. Because how do you've got this 100 million nodes and they're connected in various ways, how do you start to even begin to find out that, this group here is kind of a clump and this one is kind of a clump? Because they're all, it's not like they're beautifully connected off, right, but by themselves and have no connections out. There's actually a big messy thing. So that will be a good piece to get to, but I'll try to get into text and stories maybe even faster than that.